Assalamualaikum warahmatullahi wabarakatuh. My name is Salsamila binti Syekh Abdul Halim, supervised by Dr. Muhammad Azan, and my title for the FYP is A Study on Flow Structure Behind a Polygon-Shaped Bluff Body in a Channel Under the Effect of Constant Magnetic Field. Before we go deeper, what is the Magnetohydrodynamic MHD is? It is the study about the magnetic properties and the behavior of electrically conducting fluids, such as plasma, liquid metals, and salt water. The concept of magnetohydrodynamic (MHD) was adapted in the development of the plasma fusion reactor through the ITER, which is International Thermonuclear Experimental Reactor. The figure shows that the strong magnetic field was used to confine and control the superheated plasma away from the vessel walls inside the vacuum vessel in a torus shape called tokamak. So how the plasma was created? The concept applied is fusion nuclear physics to generate the energy. The superheated hydrogen ion, which is deuterium and tritium nuclei, collide, forming the helium and free neutron while releasing energy. Under the influence of extreme heat and pressure, gaseous hydrogen fuel becomes a plasma. Neutrons carry 80% of the energy produced in this reaction as the kinetic energy. The fusion blanket surrounding the plasma is used to absorb the heat to cool the wall facing the plasma and to transfer the heat energy to the steam generator to produce electricity. Next is the problem statement. According to Mook et al. 2000, liquid metal move under the presence of the magnetic fields that are subjected to the electromagnetic Lorentz force, resulting in change of flow pattern. The liquid metal fluid in the fusion blanket tends to be laminar because of the interaction. As we can see from this figure, the Lorentz force is the opposite to the lithium flow, which is the liquid metal. Hence, the interaction can reduce the efficiency of the heat transfer. Energy review on the effect of MHD on the flow structure. According to Krasnov et al. 2012, if Hartmann number increases, the flow becomes laminar and the turbulent layer becomes thinner. As we can see from the result from the Husam 2018, when the Hartmann number equal to 0, which means absence of the magnetic field, the flow becomes turbulent and more chaotic than the Hartmann number greater than 0. And when the Hartmann number reaches 2400, we can see the flow become laminar and the turbulent layer become thinner. Next is the effect of MHD on the heat transfer. According to Hartmann, Lazarus, and Lazarus 1937, MHD effect in reducing the performance of the thermal hydraulic fluid in a duct by increasing the pressure drop and lowering the heat transfer coefficient through the laminarization of the fluid. And according to Husam et al. 2018, heat transfer increases with increase in Reynolds number but decreases with high Hartmann number. Means MHD reduces the heat transfer coefficient of the flow. Third is on the flow past bluff bodies. According to Husam et al. 2018, triangular and square has a greater heat transfer than the circular. The triangular promoter behave better in high Hartmann numbers than square and circular. According to the data of the heat transfer increment by the Husam et al. 2018, we can see when the Hartmann number 2400, square and triangular behave better than the circular, but in comparison of the square and the triangular behave better than square in the Hartman number 2400 by 6 to 7% from the square. And according to the Shark et al. 2009 and Luo 2007, critical Reynolds number in triangular cylinder is much smaller than circular and square cylinder due to the existence of the sharp corners which alter the dynamic and instabilities of the flow. Hence, we can say that heat transfer characteristics strongly depend on the geometry of the obstacle. Next is a vortex shedding. Vortex shedding is the oscillating flow that takes place when fluid flow past a block body. A Storer number represents the velocity of the vortex shedding. According to Nisley 1989, Storer number rapidly increased with increase of the corner radius of the curvature. And according to Kazim et al., the triangle block body gives the highest vorticity among all the shapers. According to Farahi et al. 2017, Storer numbers are not dependent on Reynolds number and Hartman number, and her results show that the blockage ratio gives effects to the Storer number. The higher the blockage ratio, the higher the Storer number is. Last is the flow past triangular with a different incident angle. As we can see from the result of the Bao et al. 2010, at Reynolds number 100, the frequency of the vortex shedding increases with incident angle in range of the 0 to 90 degree. So what can we conclude from the literature review is that MHD gives a laminar effect to the flow structure and it decreases the heat transfer. In order to increase the heat transfer, the block body of the vortex promoter is inserted in the channel to increase the vortex shading so that the heat transfer can be increased. Hence, there are multiple studies according to the cylinder block body, but minimum study according to the triangle and the angle incidence of the triangular cylinder. So the objective of this study is to study the effect of incident angle of the triangle cylinder and the Hartman number on the critical Reynolds number. Second is to investigate the effects of incident angle of the triangle cylinder and the Hartman number on the Storer number. Third is to analyze the effect of the incident angle of the triangular cylinder and the Hartman number on the heat transfer efficiency. The limitation and assumption in this study is non-dimensional analysis, quasi-two-dimensional equation, incident angles range 0 to the 90, equilateral triangle cross-section was used, blockage ratio 0.25, Hartman number 0 to 200, Reynolds number 1 to 1200, Prandtl number 0.022. There are three governing equations that used in this study. First, the Magnetohydrodynamic SM82 equation proposed by the Somara and Moriel 1982 that used for the incompressible and laminar flow. Second is the energy equation. Third is the Storer number. First step is setting up the parameter, heat and length of the channel, temperature, blockage ratio, and the incident angles. Second is the geometry design. This figure shows when the incident angles is equal to 0, and the right one we can see how the triangle will rotate according to the incident angles. Third step is meshing by using Gmesh software, and fourth is set up the boundary condition. First is no slip condition, second is the inlet velocity, third is the kinematic viscosity. By using the outperform simulation, we can see the output displayed in the para view. First is the instantaneous velocity. We can see the flow structure in terms of the vorticity. Second is the temperature contour. Next is flow chart. First, the validation will be made and compared with the previous study by NG and L. And second is the hydrodynamic study, then the magnetohydrodynamic study, and then the result from the magnetohydrodynamic study and hydrodynamic study will be compared, and this is the independent variable and dependent variable that will be used in this study. That's all. Thank you.